Okay, our next speaker is Daniela Flocco from the University, speaking about melt ponds.
Good morning, everyone, and well, welcome to the last day of our talks, and I think also welcome to the last ponds presentation for this week. So, well, first of all, take into account, please, the costs at which this presentation came. So when I decided to call it like this, my Google Map and my Facebook and everything started to give me either publicity about bets, because apparently over under it gives you either guns or bets. I don't know why. So the university that Letty was mentioning is the University of Naples. So I've recently moved from CPOM at Reading University to the University of Naples. And I moved from an area of study in the Arctic to home in the UK, to area of study at home in the same place in Naples, which is my hometown actually. So I went actually from more or less that to this, with temperature at +30, and I'm working now on heat islands in Naples, which is slightly different from in terms of temperature to what I'm used to, and you actually. Through this process, I went working with Ed Hawkins in Reading, actually, doing some perfect model experiments to check on how we can improve predictions of sea ice skills by using perfect model experiments, so by using proxy with sea ice thickness, for example, by using either climatology or a proxy for real data. And we found actually that within the 15 days, we can improve predictions by almost 80%, which is very good. So we're pursuing that. And in the meantime, I also worked with Daniel on the increase in the foam drag due to the internal waves. So this is a picture from a paper that we're preparing. And this is the internal wave drag coefficient increase, which in percentage, sorry, is a bit too low, but it's up to 30% in many places in the Arctic. This is April. So the bright side of this movement has been that I went from that, which is Reading, and this is where I live now, which, the weather here is not very nice, but generally it looks like this. So I assume lots of you will want to collaborate with me now on different things. But let's get back to ponds, which has been my subject for many years, very interesting. And of course, many of you have seen these figures before, these pictures. Melt ponds are really nice, like they're very pretty things. They're blue, they're everywhere. So it's very easy to account for them in terms of the spatial resolution. I'm not saying easy mathematically, I'm saying easy because you see them. There is a lot of them. In the summer, they cover up to 80% of the first year ice, or up to 50% overall of the sea ice. You can see in these pictures as well, there are a lot of them. And yesterday, I got another one from Ellen, which is very nice because, with ponds, you can actually also look at very different features. So you can see that ponds are, for example, much wider and shallower when it comes to flat ice, and they're deeper when it comes to rigid ice. But one thing also, which you can see from this picture, that some of them have different albedo compared to others. So not only they're shallower, but very often the salinity makes a difference. So when the ponds in the summer do drain to the ocean, and there is a connection, an hydraulic connection with the ocean, very often there are algae, for example, at the bottom. Very often the salinity in those cases is higher than at the beginning of the season, or when you have shallower ponds which don't have any connection with the ocean. So this is an image from Ice Bridge, and I think, having also listened to many of these talks these days, probably some approach with some deep learning techniques might be useful to extract any more information on ponds and how they relate also to lateral meltings, and how they how they interact also with the dynamics of the ice. So as I was saying before, the first thing that, the first time that I actually started working with Daniel, this is one of the figures that was triggering all the work on melt ponds. Because what we noticed is basically, what we noticed is, I wasn't there, it was simulacron actually, that using ERS data, what was clear is that the average winter sea ice thickness was linked to the length of the season before the winter we're considering. So of course, the feature that we thought was the most important was probably melt ponds, because of course, like whatever was triggering all the melting was the albedo. So, and this paper has been published in Nature in 2003. So we went and started working on melt ponds and starting this new parameterization, which, well, some of you, most of you have listened, has been included by Elizabeth together with us in the size model. But the point is that ponds are not only the top, which is what we see. There's Niki, so they change the ice also in different ways. So this is what it looks like, from the bottom of the ponds, for example. So you see these windows. So you have light coming through. And in fact, and this is not a figure. This one, you can't really see it very well because the figure is very blue. On my computer, you see it better, but I actually drew a line somewhere. So around here, you actually see a layer of different color water, which is the mixed layer. And this is because, when there is drainage from the ponds, which are fresher compared to the ocean, you basically have a little layer of water, which is fresh and stays at the top, attached to the ice. And in fact, because of all these issues with the ponds and what happens at the bottom, and because they're also called windows, from the atmosphere to the ocean, we've also worked, this comes from, sorry, there is no reference. This is a paper by Chris Ovett with us, and this is GRL 2017. So when we started preparing this work, it was actually 5 years ago in this place. So what we've done here, it was to try and find out whether the distribution of the ponds in terms of geometry was actually making a difference to the field of light at the bottom of the ice, and it does. So it's different basically to have the same pond covered area in one pond, say even in a model, in one grid cell, or having lots of ponds homogeneously spread. So you have to get down to a certain depth in order to have the same field of light that you would have with ponds spread out differently. So as I was saying, this is the picture that I was meant to show before, the one with the line, the line where you can see actually the mixed layer, sorry, the layer of under ice pond. Not only that, because of all of these things, ponds have algae. So, in the summer you have blooms. So there are a number of ecosystem problems that probably will need to be addressed because of the presence of algae, because sometimes it's slimy, and the scan was saying they start getting into the brine, so they change the porosity of the ice at the bottom, but also they change the albedo at the bottom of the ice. And when you want to do something like in size, that you want to look at all the interfaces and you need the albedo of the interfaces, you have to take that into account, especially in certain seasons. And they freeze. So you got a pond, then it starts freezing from the bottom. The pond is a bit salty. So at some point, what you start having is that the pond creates this little brine channel in the middle, and it becomes very salty, and it messes up the gradient of temperature inside the ice at the end of the season. So as I said, they are pretty, they're very sneaky though. So from Polashensky in 2012, this is just a general but very comprehensive schematics of how a pond section will look like. So you have snow ice, you have a meltwater inflow, you have a melt pond. Melt ponds can be very small at the beginning of season. They can be spreading up to like 100 meters in size when they coalesce, and say in July, August, they cover lots of the area, so they become rather big as well. So the connection to the ocean, they can be macroscopic, so you can have like holes going from the top to the bottom of the ice, or you have a percolation drainage because the ice becomes permeable when it becomes warmer with the season, and therefore you just have a percolation going down. So I think you've seen from David at the beginning of the week that we've been parameterizing how the melt ponds behave at the top of the ice. And this is because we've always been interested, as I said before, to the albedo, to how the albedo of the surface changes. But that is not only that. So when you start looking at ponds, as I told you until now, we need to look also at what happens in the vertical direction. So the two things that I've been working on with collaborators, and this is work from Lucia Osekova, who's now University of Hawaii. She's been carrying on work in science, work that I've been studying only in like a smooth process, which is the refreezing of melt ponds. So in general, this is what we said before. So they lower the albedo, they strengthen the sea ice, the albedo feedback. So we have accelerated melt when we have ponds. But what happens at the end of the season is that if you have a gradient of temperature, which is not straight down, in the ice, you delay the basal growth of sea ice at the beginning of the freezing season. So instead of having, so you need the latent heat coming from the ocean to actually straighten the gradient that you get in the ice, which I'm going to show you now, before starting the basal growth. So say that you have at the beginning of the season a pond on top of ice, and this is the gradient of temperature. Then you get to a point where you form a lid, and the lid is going to look like something like that, because the temperature of the interface is going to be colder compared to the pond. When the pond is frozen, what you have is something that looks like that. But in order to have sea ice basal growth, you need to get to this stage. So until this negative gradient is established, you need some time, which might be days, it might be weeks, it depends on the temperature and depends on the thickness of the ice as well. So from the 1D models that we've developed, we found that it was actually even 20 days. So if time is going in this direction, and this is the temperature, so the vertical line there is the depth of the pond, and this is the ice thickness. And basically, this black line here goes like that. And compared to what we've seen before, you go from a line that looks like the blue one, so you go like this kind of L line. From that to the growth of the ice, it takes about 20 days in the simulation with the temperature we used, which were climatological ones. If you look at a section of this kind of simulation, what you see is the temperature of in the internal bit of the ice. So this is the thickness of the ice, sorry, the label is dead somewhere. So as you can see, compared to a slab of the same initial thickness, what you have is that you have warmer temperature inside the ice. So if you think about the size model, where you have layers of ice with different. Oh, thank you. I thought, I have that. So stupid. I have this. I always need Daniel. So as I was saying, so if this is the pond, which is freezing, and then it's becoming like, thickness 0, then, like this, what happened here actually propagates deeper and further in time compared to this case, where you just have sea ice, which at some point, because of the gradient of temperature between the air and the ocean, is going to grow. So the point is that if you think about size, it's too simplistic to just assume that the pond is going to freeze and you just get this piece of ice at homogeneous temperature and you stick it there. You can't do that. I mean, we have, because, as a first attempt, that was a good thing to do. But what Lucia has been doing, carrying on from this work, is that she's actually modeled all the different layers and in all the different cases. So basically, this is the development of the new pond parameterization we have now in size 5. So you start at the beginning of the season with no ice, then you get to, you form a pond. At the end of the season, you form a lid. On the lid, you get snow. And when the pond is frozen, you end up in this situation where the only difference is that this lid is physically and in temperature very likely for a bit going to be different from this case. And then you circle around after winter. So in the first thing is the snow ice situation, then you form the pond, and there is a modified surface balance because compared to what we've done before with size, I think in the official release, what we have now is still a change only in the sea ice albedo, but there is no change there is a conservation of quantities like, like sea ice volume, but there is no conservation for the temperature. You will change the temperature in a hardwired manner. Well, in this case, we have the equations which calculate the right temperatures at all the interface that we have in all the different cases. So what Lucia has done is to adjust all the interfaces by using the new conductive heat flux in the pond with the 4/3 law, and she's added it here in the new surface energy balance and in the pond equation. So when you have the refreezing itself, you basically have this kind of situation. So this is a simplified 1D simulation. It means that basically she's run size fully, but then she's taken the routine for the ponds out to check properly what was happening only for the, just to check, how the routine was working. It was more a sensitivity study. So you can see here, how the thicknesses are working. So if you look at the base of the ice, it's always the same. So if you look at the pond is going to decrease in thickness while the lid is going to grow. And the liquidus temperature here is going down in time. So this is 2 weeks. But the salinity of the pond, since the pond is getting smaller and smaller, and salt is basically getting into the remaining volume of water, the pond salinity is going up. And it's almost like an asymptotic curve that up to, well, in this case, like 300, but values that I've seen are more like 80. They're not that high. So if we look at the full-size simulation, but only look at one grid cell, because of course, these processes are very local. So we haven't, we've done some of the results, for more like climate change scopes. But in this case, what I wanted to show you here is that, so you see that more or less in the middle of July, August, you have a lid which starts forming like this. And the top of the pond thickness is going to be more or less at the same time. So, well, there are a number of mathematical bits and pieces which I'm happy to discuss later, but there are little adjustments because of course you have to make sure that things don't go crazy with size, just technically, just because if the lid is too small, if there is too little water, these kind of things. So, same thing, this is for another location, but again, you can see that the pond salinity evolves over time and it modifies the liquidus temperature. So the pond depth over the sea ice area, so this is over the whole grid cell, so you need to divide by the ice area to get the right number. And this is the salinity, so this is more what we get into the code. So you have values that go up to 80 or 90, and this is one of the highest that we see in the results. So then the ponds refreeze, and we get back to the situation that we've seen before. So before refreezing, we get this, and then suddenly, this curve has to then be combined in terms of the temperature profile, so that after refreezing, we get this, and then size takes care of the evolution of the temperature. But this is what is interesting. So if we look at all the layers, the vertical layers in size, what we see is that with the new control run, with the new run compared to the old one, when we had the freezing onset here, we still saw that there was a delay in the basal growth of the ice. But basically, now, by looking at how properly the temperature evolution is implemented in size, there are about almost 2 months in which there is no basal growth. The temperature is actually quite high here compared to the control run. And when the melt pond is frozen, this is when the temperature starts going down, and this is when the basal growth starts. Of course, we're talking about the location when this happens. So I would like to click these things at the same time, or almost, because here we have the evolution, the spatial evolution of the melt ponds over sea ice and the list thickness. So it would be nice to see. This is going from June 2008. So you can see the melt pond depth. And now as soon as you hit August, September, you start seeing how the lid is forming, and how, when the ponds are still present, you still have, volume of water, but that volume of water is not really changing anything in terms of the albedo of the surface. So, as preliminary results, what we see is that one of the parameters that really makes a difference in terms of the anomaly of the volume of sea ice is this one. So when we look at the surface energy balance, this value, this term is telling us how much surface radiation is taken, not right at the interface, but within the first 10 centimeters. And this value within the pond seems to make a difference in the sea ice volume in the global simulation. Now, since I've been too slow on this, I just want to talk to you briefly about the under ice melt ponds, because I promised I would. So, under ice melt ponds, they form around here. They're fresh. Very often, something, ice forms at this interface. Exists, and like Bruno was saying, sometimes you have to stick something through them to actually get to the ocean. So there are various stages for which the false bottom forms. There is fresh water, and there is ice forming at the interface. They coalesce and they do something like this. So you have false bottom, and what I wanted to show you is that what happens is that you might either, depending on the initial condition that you have here, which might be salinity or temperature of the water, the under ice pond is either going to have a false bottom, which is going to cover it up. But if the pond becomes too salty, for example, the pond is going to break through the ice and is going to melt the false bottom. And this has actually consequences on the sea ice thickness at the end of the season. But also, if you have a mixed layer, what you see is that when you have an under ice melt pond, this is not very, when you have an under ice melt pond or a slab, you actually have a difference in the mixed layer depth when you couple a slab ocean under the sea ice model. These are process studies, so these are small models that we've written, then this is not size. In terms of impact, the sea ice could have an impact in terms of thickness of volume up to 3%, which is not very much, but still, in terms of getting things right, which is what we want to do in terms of the physics, accounting for all the phases that we have when you have ponds is actually very important, because of course, if it is true that melt ponds are so widespread, overwhelmingly widespread, and between 5 and 40% of the melt ponds would have an under ice pond. If you don't account, even if you account for advection of water, which is going to blow away, the layer of fresh water you form at the bottom of the ponds, you still have Well, we've accounted, just to be conservative, up to 3.2% additional sea ice volume. So these are considerations that we're working on. So there is a possible feedback cycle. So, between the refreezing and the under ice melt ponds, the point is that calculating the sea ice balance and the sea ice mass balance when you have ponds is not trivial. It's not just to add ice. You have to consider lots of thermodynamics going on, and dynamics actually. So I'll finish with this, and thank you for your attention. I'll be happy to take questions.
Questions?
Thank you for the very interesting talk. Just a question about the through melt ponds. What do you think about that part?
Well, this is why I was talking about, probably having to use different techniques. Because when you look at these figures, like, the ice bridge ones, you have to decide whether you want to use that to find out what is the salinity of the ponds. Because, it might be that just visually we'd be able to work out, what kind of ponds we're talking about. But, there is no way to look at the single ponds. That's the point. It's always, it's always the same issue. So you can't really distinguish, and you can't really discriminate sometimes whether a pond is actually dark because there is a macro hole which is just melted through, or it's because there is just an hydraulic connection, so water from the ocean is going through and you got algae, and so that's why it's dark. But they do get very mushy. So I've seen lots of pictures. They become very dark at the bottom towards the end of the season. Wow.
Thank you. I wondered what the effect of this freshwater layer was. Is that not going to make the freezing faster again when when winter comes?
If it stays there, yes, it does. So it depends basically on what kind of process happened. So, if you got the layer of the ice, it forms, it stays there, it will insulate that layer of water inside. It is going to completely freeze. If it doesn't, still that water is going to freeze faster because it's fresher. The point is, if you have currents, that layer of water is easily going to be just advected away. So that's why I say it's not obvious,
Daniela, very nice talk. Did I see correctly that you showed a graph of the pond salinity with values of about 80
yes.
on it? And how does it get so salty?
Because the salinity of the pond at the beginning is up to, well, like very often is 1.2, it can be 3. Sometimes there is just, splashes of water going from the ocean into the ponds. So you can have different salinities. Or if you have percolation, there's been observation of 28 or 29 PSU. So of course, once you start refreezing the ponds, they almost become like brine pockets, basically. So they tend to become very, very small. So there was a picture there, you could see the dendrites forming because, it was right at the beginning, I think. This is probably the only pictures I've seen, and I asked for it a few years back. Yeah, this one. What I found. So you see the dendrites here. And this is a pond which is refreezing. So you get this dome in this case, for example, and slowly you get the ice going through. Well, there is an experiment. I didn't show it here. That shows how also, all these things form. So, generally, whether, tell me about this, about how these spickles of ice start forming just like that in these kind of situations. And also in the false bottoms, they behave like that.
One question over here.
Thank you for your talk. So my question is directly linked to the one that have been already asked. It's so you have a segregation of the water that freeze, and underneath or overneath you've got some salt that is crystallized, if you understand correctly.
Well, it's not salt that is crystallized. You know, actually, when you start okay, you're talking about the pond at the top or at the bottom. But in both cases, anyway.
Actually, any of these, because I don't really know the phenomenon. It's one of the first time that I heard about
okay,
it.
So if you start, you start, for example, from the top, the air becomes cooler. So either, for example, you have snow that starts cooling also the water in the pond, and you form a layer at the top. So that layer is fresher. Sea ice, when it forms, releases salt. So it's fresher than the water that is coming from, which is why you get this kind of situation. While instead at the bottom, you got a layer which is relatively fresh, but it's much fresher than the ocean water. Because the ponds originally come from snow melt. You know, they're rather fresh, but not completely, which makes all the difference.
Thank you, Daniela. I just wanted to clarify a couple of things. So those high salinities in the refrozen pond that Gray was raising his eyebrows about, I can tell from here. Okay. So, okay, yes, it is surprising. Okay. Yes, it's also observed. Okay. So it's not, there's some verification of this. Okay. And actually, the experiments go back to, I think it's, I think maybe Seeley back in 1970 or something did some experiments.
I think so.
Yeah, but also, yes, it was very nice. Also, we've measured it in ice tanks as well. So we've decades later saw the same thing. Okay.
Yeah, I think there is also some. I think it was Marchenko and all.
Yeah,
you know,
yeah.
They did quite a few experiments, you know, like engineering, because, well, you remember, you know, when Ellie was doing
Sure.
her PhD, they've done quite a bit of that.
The other thing I was going to say is that this business about the under ice melt ponds refreezing, what can happen is when they melt through eventually, you suddenly have a reservoir of fresh water being released into the mix layer. Okay, and that can dramatically shallow the mix layer when that happens. So if you have a simulation with and without under ice melt ponds, and we've simulated realistic under ice pond fractions, it can have an impact on the mix layer of around 10 meters or more, and shallow the mix layer about 10 meters or more. So it can have actually quite significant impacts, at least in our very simple ocean mix layer model. But I should probably shut up now.
Well, that depends also, you know, on the size of the pond, of course, you know, because if the hollow of the under ice pond is quite, say, protected by the currents, you get quite a lot of, you know, quite a bit of water, volume of water, which is kind of can be released suddenly. Anyway, thank you.
Okay, thank you. Let's move to our next speaker.